start electrochemistry. We have to start. Okay, today. Yes. Okay. The next topic, electrochemistry. Okay. Right. So electrochemistry is very familiar for you because you already studied lot of things in your school. Most of the students maybe come from the CBSE background, means they are very familiar in that electrochemistry. The same only we are doing here also. First, what is a electrochemistry? Electrochemistry means what? What is the electrochemistry? Say loudly. Why? No issue. Everyone is okay. You are second year, second semester, still the same shyness. What is the electrochemistry? Electricity is used to say anybody? Okay, everything we can discuss from the title itself. Chemical energy convert to electrical energy, that is electrochemistry. Normally the chemical energy is given the electrical energy means that is electrolytic cell. And using the electrical energy we do the chemical reaction also, that is voltaic cell. Voltaic cell and electric cell, electrolytic cell. Okay, you know that for our mobile batteries, when charging the mobile batteries, using the electrical energy, the chemical energy is doing. Okay, and using the chemical energy, when after charging we can use the mobile, that is a electrolytic cell. Okay, electrochemical cell, electrolytic cell. Electrochemical cell means using the chemical energy we get the electrical energy, that is electrochemical cell. Using the electrical energy we do the chemical reaction means that is a electrolytic cell. Okay, this is a electrochemical cell. Electrochemical cell. Okay, this is electrolytic cell. That's why all the rechargeable batteries it act as both. Even the lead acid battery, lorry batteries, car batteries. Okay, we pour some electrolyte. The concentration decreasing when using continuously. Therefore, they can pour the electrolyte and charge it again. We can use it. Lead acid battery. Okay, so it acts as both electrochemical cell as well as electrolytic cell. Okay, when chemical energy given the electrical energy means that is electrochemical cell. Using the electrical energy we do the chemical reaction means that is electrolytic cell. Okay, electrolytic cell. Yes. So here the electrochemistry, the production of electricity, one main thing, the production of electricity during the spontaneous chemical reaction, that is main. Okay, production of electricity during the spontaneous chemical reaction, that is main. Without given any external energy, the reaction is spontaneous. That time it produces the electrical energy means that is good electrochemical reaction. Okay, then you know normally the electrochemistry normally deals with the redox reaction only. Yes, it deals with only the redox reaction, right? Redox reaction. You know that electrochemical series, there the reduction potential given, not oxidation potential, reduction potential may be based on the sign variation, plus and minus. See, in the neutral potential, that is zero potential, what is that? Which element is a zero which one is a 0 volt? Reduction potential value is 0. Which element? From that only we comparatively say that is a reduction potential, oxidation potential. Which one is the middle one? Hydrogen. Hydrogen is the reduction potential value is 0. Okay. Hydrogen reduction potential value is 0. Based on that only we say the zinc and the copper. You know the zinc and the copper. When we connect zinc and the copper, what is that cell? We connect zinc and copper in the electrochemical reaction. That is a basic cell. When you read the electrochemistry, basic cell is the copper and zinc. You connect. What is that cell name? Daniel cell. Daniel cell. Okay, copper and zinc. When you connect the copper and the zinc, how much volt you get it? Huh? No. Too much. When you connect the copper and the zinc, how much volt you get it? Normally, how much volt is there? .1 volt. Okay. For example, yeah. See, look at here. Okay, this is a zinc rod and this is a zinc sulfate SO4 solution, and this is a copper rod, this one copper sulfate solution, and this is a salt bridge. You know salt bridge. Salt bridge. This is a voltmeter. Okay, voltmeter. This is a Daniel cell setup. Right, Daniel cell setup. So here the zinc act as a anode, copper act as a cathode. In the zinc side or else the anodic side, oxidation happened. In the cathodic side, the reduction is happened. That means here the electron donate, here the electron accept. That is a oxidation. Here reduction. Okay, here reduction. So that time when the electron move from the anode to cathode, you get the current, you get the volt, 1.1 volt. Okay, 1.1 volt. So there the zinc is oxidized. So their reduction potential is minus 7.6 volt. When zinc becomes zinc 2 plus, there you get the minus 0.76 volt, and similarly when copper get the electron from the zinc, therefore Cu2 plus accept 2 electron to form a copper, there you get the 0.34 volt. So approximately total volt is 1.1 volt. You get it? Okay, 1.1 volt.
Sir, can you repeat about?
Yeah, that's what. At anode. Okay, at anode what happened? Zinc to become zinc 2 plus 2 electron. Okay, zinc 2 plus 2 electron minus 0.76 volt. Okay, at the cathode what happened? There the reduction is happened. This is the oxidation. Oxidation, here reduction. So at cathode copper 2 plus. Copper 2 plus is there in the solution state. That is the electrolyte. That copper 2 plus get the electron from the anode where it's come from the anode 2 electron to form a copper. Their reduction potential is plus 0.34 volt. Okay, 34 volt. What is a net cell reaction? What is a net cell reaction? So here 2 electron cancel, therefore zinc react with copper 2 plus, it convert opposite, that is zinc 2 plus copper. Your net volt is 1.1 volt. This is a net reaction. Net reaction. Right? This is a Daniel cell reaction. Daniel cell setup. When we connect the zinc and the copper together, we get 1.1 volt. Okay, 1.1 volt. At the anodic side, oscillation is happened. At the cathodic side, reduction is happened. In the anodic side, we measure only the reduction potential. Therefore, here oxidation is happened. We connect the zinc rod into the standard electrode, hydrogen electrode. There we find that how much reduction potential be 0.76 volt. So here zinc is oxidized. Hence you change the sign minus 7.6 volt. Okay, minus 7.6 volt. So here what happened? The two off cells we connect each other, we get one cell setup. Okay. The individual cell potential we should not calculate, or we should not get the individual cell potential. We connected one off cell with the hydrogen standard electrode. Then we find what is the reduction potential value of the second off cell. Okay, second off cell. That's why the Taylor column given everything with the standard hydrogen electrode. Compared to standard hydrogen electrode, easy to reduce or very tough to reduce. That's it. That table says compared to hydrogen electrode. The hydrogen is a sea level. Below the sea level or above the sea level, that's it. Hydrogen is 0. Here the zinc copper 2 plus is plus 3.4 volt and zinc is minus 7.6 volt. So below and above the sea level, that's it. So everything we compare with one standard. Here we compare the hydrogen as a standard. So for example, in our class, who's the third rank, who's the fourth rank means how you can say compared to first rank, who's the second, who's the third. One reference always will be there. With that reference only we can claim I am the second, I am the third, I am fourth. So therefore one reference is there. That reference is there. Here hydrogen electrode. Hydrogen electrode. Okay, right. Two off cell connected internally through the salt bridge. You write it below this. You write it. Two off cell connected internally two off cell connected internally. Okay, two off cell. This one off cell, that is a copper off cell. This is a zinc off cell. Through the salt bridge. Here, what is the role of the salt bridge?
Which one? Which make sure that both are
Yes. It more loud. Tell me, yes, it is correct. What you are saying. Maintain. What is the role of salt bridge? it maintains the concentration of both anodic side and cathodic side. Okay, it maintains the concentration of anodic side or cathodic side. Otherwise, it maintains the ionic equilibrium, both sides. That is the main ionic equilibrium. Because when the reduction is happened, yesterday it's very clear. Now, why this one? See, listen. When here oxidation is happened, what happened here? Increasing the concentration of zinc, right? Here increasing the concentration of zinc 2 plus ion continuously. When reduction is happened, here decreasing the concentration of 2 plus ion. Here decreasing, here increasing. Therefore, the salt bridge is equalize both the sides. That's why after some time we add the electrolyte manually for our rechargeable battery also, lorry battery. After some time they can go for the battery shop, they can add the electrolyte. There the sulfuric acid as a electrolyte. Okay, lead acid battery. Okay, sulfuric acid. So here the zinc 2 plus and copper 2 plus, here decreasing, here increasing the copper, zinc. So it maintains the ionic equilibrium, that's why the salt bridge is there. If here continuously increasing the zinc 2 plus ion, what happens? It won't oxidize. Because more zinc 2 plus ion, then compare with the sulfate ion. Okay, right. Now, there are two off cell connected internally through the salt bridge. A potential difference develop. Yeah, that is the main point. The potential difference. Potential difference. Okay. Potential difference develop between the electrode with the electrolyte. The potential difference is there. Electrode and electrolyte. Electrode and electrolyte. So the potential difference is there with the electrode and here the zinc rod is there. Okay. Here zinc sulfate solution. Zinc sulfate solution. This is a zinc rod, right? So here the potential difference will be there with that electrode and electrolyte. That is called, how we can call this one? That is called what? The potential difference definitely will be there. That way the zinc comes to zinc 2 plus. Okay, here the zinc rod corrode. Continuously the zinc rod corrode continuously. So therefore that potential difference called electrode potential. Okay, that potential difference is called electrode potential. Okay, electrode potential. Okay, electrode potential. Yeah, so next point you write it. When the concentration of all the species, you write it. The concentration of, next point, the concentration of all the species involved in the concentration of all the species is unity. The concentration of all the species is unity. Then the electrode potential called standard electrode potential. Then the electrode potential called standard electrode potential. Then the electrode potential called standard electrode potential. Okay, standard electrode potential. So here the zinc is a one half cell, copper is a one half cell. You connect the two half cells, you get the cell potential, net potential. Cell potential means that is called your cell potential, not for the half cell potential. Half cell potential we find it based on your hydrogen reference electrode, standard hydrogen electrode. Okay, whatever you get it, this one is a half cell potential. Yes, student, listen. This one called half cell potential. When you connect the two half cell, you get the cell potential. Okay, listen. When you connect the two half cell, you get the cell potential. That cell potential, how we can calculate? E cell equal to E right minus E left. E right minus E left. E cell potential equal to, that is reduction potential of cell. Cell reduction potential equal to E right minus E left. E right minus E left. So in the E right, what happened? E right side, cathode, reduction. Okay, and the E left, oxidation. So therefore, how you can write it? E copper 2 plus becomes copper minus E zinc 2 plus become zinc. Or else reduction minus oxidation. Reduction minus oxidation. Okay, reduction minus oxidation. Normally the half cell potential, the potential of individual cell, we should not measure. The zinc, what is a cell potential? No, we should not measure. Always we connect that zinc electrode into the standard hydrogen electrode, then only we can calculate the reduction potential of that half cell. Okay, half cell. So individual cell potential we should not measure, hence we connect the standard hydrogen electrode, then we can find it what is the reduction potential of the second half cell. Right? And that's why we say the standard hydrogen electrode, standard hydrogen electrode, the standard hydrogen electrode, we connect with the half cell. Half cell. Then we find it what is the reduction potential of the half cell potential. Okay, right. So that's why we say, for example, platinum, that is solid, hydrogen H2, we can pass the H2 gas. Okay, it becomes H plus ion because we take given the electron from the other side, right hand side, and here copper 2 plus, that is aqueous, that is solution state, comes to copper reduction solid state. What is a cell reaction? Cu2 plus that is aqueous, okay, plus 2 electron to give copper. The E cell value is E cell equal to E right minus E left, right? Therefore copper 2 plus becomes copper minus standard hydrogen electrode. So here 0.34 volt, 0.34 volt minus 0 is equal to 0.34 volt. So what is the meaning of that 0.34 volt? What is the meaning of that? It indicates the copper 2 plus. It indicates copper 2 plus is easy to reduce than hydrogen. Then listen. Then hydrogen. So here this is a cell representation. You know the cell representation. We should not draw the cell setup always, right? In the beaker and we should not draw the beaker and here the anode, here the cathode. We should not draw always like this. Instead of that, we can write the cell representation. The cell representation exactly matches your cell setup. This is a cell setup. This is a cell representation. This is a cell reaction. Okay, cell reaction. What happened in that cell? That we can write it. The reaction, cell reaction. Here, this double slash indicate what? Here, this one, salt bridge, and here, this one indicates the single slash indicates this is a salt bridge. Okay, this one. Single slash indicate what? Phase changes. Solid to liquid. Solid to gas. See here. Solid. You know the platinum. Platinum has a solid surface. Okay. We can pass the hydrogen gas. We touch the hydrogen gas. So what happened? That hydrogen gas is deposited on the platinized surface. Okay, then the oxidation is happened. That is hydrogen 2 becomes H plus. Then only the electron is released. That electron is go for the cathodic side. It get the electron from the hydrogen to reduce copper 2 plus to copper. This is a phase changes. Aqueous phase to solid phase. Single slash. So your left hand side oxidation, right hand side reduction. So we find always the reduction potential only. Here the reduction potential is 0.34 volt. That meaning is compared to hydrogen, the copper is easy to reduce. Otherwise the electron is coming here, right? So this is a feasible reaction. This is not a feasible reaction. But in the case of other zinc minus 7.6 volt, that means compared to hydrogen, compared to zinc, hydrogen is easy to reduce. But here it indicates the copper 2 plus is easy to reduce than the hydrogen. Otherwise, why the hydrogen is donated electron to the cathode? No. It gets the electron from the copper. In the case of zinc, like that. Instead of the zinc reduction, it gets the electron from the zinc. That's why we can indicate the negative sign, minus 7.6 volt. Okay? Yes. So, platinum is a main for your hydrogen electrode, because in the platinized surface only the hydrogen gas is absorbed on the surface of platinum. Then the absorbed hydrogen only to donate the electron to the cathode. That time the H2 becomes H plus ion. Okay, H plus ion. That's why when you pulse the hydrogen gas in your anodic side, the bubbles coming. Okay, bubbles coming. So there the hydrogen H2 gaseous is there. There the hydrogen gas is deposited, absorbed on the surface of platinized. So there the H2 becomes H plus ion. So when H2 becomes H plus ion, what happens? You get the 2 electron, because 2 moles of hydrogen. So 2 H plus 2 electron. That 2 electron is to come for the cathodic side. Right? Clear? You got it? Otherwise, hydrogen cannot oxidize. Otherwise, hydrogen is not oxidized the copper. Any of meaning is easy to reduce the copper than the H plus ion. That's it. Right? Now you arrange copper, hydrogen, zinc. Copper, hydrogen, zinc in the order of reduction potential. Which one is easy to reduce? Which one is tough to reduce? You arrange copper, hydrogen, zinc. Copper 2 plus hydrogen and zinc. Which one is easy to reduce? What is the reduction potential value of copper? What is the reduction? Cu2 plus.
0.3.
Cu. You are saying Cu. What is the reduction potential value of Cu? 0.34 volt. This one 0. This one minus 7.6 volt. Okay. So which one is easy to reduce means copper. Which one is easy to reduce means hydrogen. So from that reduction potential value, you understood positive means easy to reduce then the hydrogen, then the reference metal. Here negative means hydrogen is easy to reduce than that negative potential metal. What is the time? Similarly, I can give some of the metals you arrange as per the reduction potential order. Okay, that is K plus becomes K minus 2.93 volt. Ag plus becomes Ag 0.8 volt. Mercury becomes 0.79 volt. Magnesium 2 plus becomes magnesium. Okay, you arrange this reduction potential value similarly. Okay, which one is easy to reduce? That order you follow, you arrange accordingly. Right?
Sir,